Welcome to this scientific lecture on field-driven pumping mechanisms in real microfluidic chips. Today we will explore why predicting fluid flow in these systems is extraordinarily challenging. The central problem is this: in real chips, multiple electrokinetic effects overlap. We have alternating current electroosmosis, electrothermal flows, induced charge effects, and more. These mechanisms do not operate in isolation, and separating them cleanly to predict net flow remains one of the hardest problems in microfluidics. Picture a microchannel between two electrodes. Apply an alternating electric field. What happens? Multiple flow mechanisms activate simultaneously. Some flows point one direction, others point the opposite way. The net result is a complex superposition. Let's start with a fundamental question. Why do we use alternating current fields instead of direct current? Why not just apply a steady voltage? Direct current fields cause electrolysis at the electrodes. Water molecules split into hydrogen and oxygen gas. Bubbles form, blocking the channel. This is catastrophic for microfluidic devices. Alternating current fields, especially at frequencies above 1 kHz, avoid electrochemistry. The field reverses before significant charge transfer occurs. This is why ACEO electrokinetics dominates modern microfluidics. So we have a channel filled with electrolyte solution. Two electrodes on either side apply an alternating voltage. The field penetrates the fluid. Now multiple physical mechanisms activate. The first mechanism is ACEO electroosmosis, abbreviated ACEO. This is perhaps the most important pumping mechanism in microfluidics. ACEO occurs very close to electrode surfaces, within the electric double layer. When you apply an AC field, ions accumulate near the electrode, forming a double layer. The field then acts on these ions, creating a slip velocity. Here is the electrode surface. Positive ions accumulate on one side, negative ions on the other. The tangential electric field acts on this charge distribution, generating a slip velocity. The fluid above is dragged along, creating a pumping flow. The key scaling is that the slip velocity is proportional to the square of the electric field. This is a nonlinear effect. Double the voltage, you get 4 times the flow. This quadratic scaling is characteristic of ACEO. The slip velocity is proportional to E squared. ACEO has a frequency dependence. It is strongest at intermediate frequencies, typically between 100 Hz and 100 kHz. At very low frequencies, the double layer fully charges and the effect weakens. At very high frequencies, the double layer cannot form, and again the effect weakens. The second mechanism is electrothermal flow. This arises from temperature gradients in the fluid. When current flows through the electrolyte, Joule heating occurs. The fluid heats up, especially near regions of high current density. This creates temperature gradients. Here is a hot spot in the fluid. Temperature is highest at the center. Temperature gradients cause gradients in permittivity and conductivity. The electric field then acts on these gradients, creating body forces that drive flow. Two fluid properties vary strongly with temperature. First, the electrical conductivity increases with temperature. Second, the permittivity decreases with temperature. These competing effects create complex force distributions. The electrothermal force is proportional to the gradient of conductivity times the electric field. Electrothermal flows become dominant in highly conductive fluids. In biological buffers with high salt concentration, electrothermal effects often overwhelm ACEO. This is a major challenge because biological applications require physiological salt levels. The third mechanism is induced charge electrokinetics. This involves polarizable objects in the fluid. When you place a conducting or polarizable particle in an electric field, it polarizes. Charge accumulates on its surface. This induced charge then interacts with the field, creating flows around the particle. Here is a metallic particle in an electric field. Negative charge accumulates on the left side, positive on the right. The induced double layer forms. The tangential field then acts on this induced charge, creating slip flows around the particle. Induced charge electroosmotic flows, or ICEO, exhibit a characteristic quadrupolar symmetry. Fluid is pumped toward the particle at the poles and away from it at the equator, or vice versa depending on field direction. The ICEO velocity scales with particle radius times e squared. Here is a critical question. Can we separate these mechanisms experimentally? Can we design an experiment that isolates ACEO from electrothermal from induced charge effects? The answer is extremely difficult. All three mechanisms respond to the same applied field. They have different frequency dependencies, but their ranges overlap. They have different scaling with conductivity, but changing conductivity affects multiple mechanisms simultaneously. Here is the reality. ACEO pushes fluid to the right. Electrothermal flow pushes to the left. ICEO creates local circulation. The net flow is the vector sum. Predicting this sum from first principles is extraordinarily hard. Let us do a back-of-envelope calculation to compare ACEO and electrothermal magnitudes. This will give us intuition about when each dominates. Consider typical parameters. Applied voltage is 1 volt. Channel length scale is 100 microns. Frequency is 10 kHz. The electric field is voltage over length, 1 volt divided by 100 microns, which gives 10 to the 4 volts per meter. The ACEO velocity scales as epsilon times v squared divided by eta times L, where epsilon is permittivity and eta is viscosity. Plugging in numbers. Epsilon is about 10 to the negative 10, v squared is 1, eta is 10 to the negative 3, L is 10 to the negative 4. This gives about 1 mm per second. Electrothermal velocity depends on Joule heating. The temperature rise scales as sigma E squared times L squared divided by thermal conductivity. For moderate conductivity, sigma is 0.1 Siemens per meter, E squared is 10 to the 8, L squared is 10 to the negative 8, thermal conductivity K is 0.6. Temperature rise is about 0.2 Kelvin. The electrothermal velocity is then about 0.1 mm per second. So ACEO dominates, but only by a factor of 10. Now increase conductivity to 1 Siemens per meter, typical of biological buffers. Temperature rise increases by a factor of 10. Electrothermal velocity jumps to 1 mm per second. Now they are comparable. At even higher conductivity, electrothermal wins. This is exactly why predicting flow is hard. The relative importance of mechanisms depends sensitively on conductivity, frequency, geometry. Small changes flip which mechanism dominates. Frequency dependence is perhaps the best tool we have to separate mechanisms. Each effect has a different frequency response. Plot velocity versus frequency on a log scale. ACEO has a peak at intermediate frequencies, typically kHz range. Below this, double layer charging is too slow. Above this, the double layer cannot form. ACEO peaks around the RC time of the double layer. This time is lambda d squared over d, where lambda d is the Debye length and d is the ion diffusivity. For typical electrolytes, this gives a characteristic frequency of kHz. Electrothermal flow is most active at low frequencies, below 1 kHz. At low frequency, there is time for heat to diffuse and create gradients. At high frequency, thermal inertia suppresses temperature oscillations. Induced charge effects also peak at intermediate frequencies, similar to ACEO. The particle polarization time sets this scale. Unfortunately, this means ACEO and ICEO frequency ranges overlap, making them hard to distinguish. Let us discuss complications that arise in real chips but are absent from idealized theory. Surface roughness matters enormously. Electrodes are never perfectly smooth. Roughness features create local field enhancements. These hotspots drive strong local flows that dominate the average. Here is a rough electrode surface. Each asperity acts as a tiny pump. The field concentrates at sharp features. Flow velocities near these features can be 10 times larger than the smooth surface prediction. Electrodes age over time. Oxidation layers form. Proteins or particles adsorb. The effective surface properties change. An ACEO flow that worked perfectly yesterday may fail today because the electrode surface has changed. Most real devices are three-dimensional. Electrodes are not infinite planes but finite patches. The field distribution is three-dimensional. Flows develop complex three-dimensional patterns that are nearly impossible to predict analytically. We have not even mentioned concentration polarization. When ions move, their concentration changes. This creates concentration gradients. These gradients affect conductivity, which affects the field distribution, which affects the flow. It is a fully coupled problem. Apply a field. Ions migrate. Positive ions move right, negative ions move left. Depletion zones form on one side, enrichment zones on the other. The local conductivity changes by orders of magnitude. The field redistributes. Everything couples together. Given all this complexity, how do researchers actually cope? How do we design devices when prediction is so difficult? Strategy 1 is empirical optimization. Build many devices, test them, iterate. Use design of experiments methods to explore parameter space. This works but is expensive and time-consuming. Strategy 2 is numerical simulation. Solve the coupled Navier-Stokes, charge transport, and heat equations numerically. Modern software can handle this, but the computations are expensive and require accurate material properties. Strategy 3 is asymptotic analysis. Identify small or large parameters. Expand the solution in these parameters. This gives analytical insight into which mechanisms dominate in which regimes. For example, the thin double-layer limit. When the Debye length is much smaller than all geometric scales, the double layer appears as a boundary condition. This simplifies the problem enormously and is valid for most microfluidic applications. The thin double-layer limit. Debye length much less than channel size. Let me describe some clever experimental techniques that help isolate mechanisms. Technique 1. Conductivity sweep. Measure flow velocity as a function of solution conductivity. ACEO is relatively insensitive to conductivity. Electrothermal scales linearly with conductivity. This allows you to separate their contributions by fitting. Plot velocity versus conductivity. ACEO gives a flat line. Electrothermal gives a line with positive slope. The measured data is the sum. By fitting, you can extract both components. Technique 2. Frequency sweep. Measure flow as a function of frequency from 1 Hz to 1 MHz. Different mechanisms have different peaks. Fitting the frequency response to a model can identify which mechanisms are active. Technique 3. Particle tracking velocimetry. Seed the fluid with tracer particles. Track their motion with a microscope. This gives you the full velocity field, not just an average. You can see the spatial structure of the flow, which reveals the underlying mechanism. Let us work through a concrete case study. Consider a parallel electrode array used for pumping. This is a common geometry. 4 parallel electrodes. Apply an AC voltage with a phase shift between adjacent electrodes. This creates traveling wave fields. The idea is to pump fluid from left to right. The phase shift between electrodes creates asymmetry. Without it, each electrode pair would pump symmetrically and produce no net flow. With phase shift, you break symmetry and get net pumping. At low conductivity, ACEO dominates. You get strong pumping, velocities of millimeters per second. Everything works beautifully. At high conductivity, electrothermal becomes strong. Worse, it often pumps in the opposite direction. The net flow reverses. Your pump becomes a pump that pushes the wrong way. The crossover conductivity where flow reverses depends sensitively on geometry. Electrode width, gap size, channel height all matter. Predicting the crossover point requires detailed simulation. Let me give you a quantitative example with real numbers. Electrode width is 50 microns. Gap is also 50 microns. Applied voltage is 1 volt at 10 kHz. The electric field in the gap is roughly 1 volt over 50 microns, which is 2 times 10 to the 4 volts per meter. For a water-based electrolyte at low conductivity, say 0.01 Siemens per meter. ACEO velocity is about 1 mm per second. Electrothermal velocity is only 0.05 mm per second. ACEO dominates by a factor of 20. Now increase conductivity to 0.1 Siemens per meter. Electrothermal jumps to 0.5 mm per second. Still smaller but now comparable. At 1 Siemens per meter, typical of phosphate buffered saline. Electrothermal velocity is now 5 mm per second. It dominates. If it pumps opposite to ACEO, net flow reverses. Let us talk specifically about induced charge effects around particles. This is important for applications like particle manipulation and separation. Around a polarizable particle, the flow has quadrupolar symmetry. Fluid is sucked in at the poles and expelled at the equator, or vice versa. This creates a characteristic pattern. The flow direction depends on particle conductivity relative to the fluid. If the particle is more conductive, you get one flow direction. If less conductive, the flow reverses. If particle conductivity exceeds fluid conductivity, you get flow in one direction. If particle conductivity is less than fluid conductivity, flow reverses. This enables separation strategies. Particles with different conductivities experience different flows. They can be separated based on their electrokinetic response. Now an advanced topic. At high fields, nonlinear responses appear. The simple quadratic scaling breaks down. Ion steric effects limit how much charge can pack into the double layer. Ions have finite size. At high voltage, the double layer becomes crowded. The capacitance saturates. At very high field, electroconvection instabilities appear. The flow becomes turbulent. Vortices form. This is an active research area. At high voltage, the flow becomes chaotic. Vortices appear everywhere. The system is no longer laminar. Predicting flow becomes essentially impossible without direct numerical simulation of turbulence. So here is the big question. Given all this complexity, can we ever predict flow accurately from first principles? Or are we doomed to empirical approaches? The answer is, it depends on the regime. In limiting cases where one mechanism clearly dominates, yes, we can predict accurately. ACEO in low conductivity fluids at intermediate frequency is well understood. But in transition regimes where multiple mechanisms compete, prediction remains hard. Small uncertainties in material properties propagate into large uncertainties in flow. The future lies in better models that include all relevant physics, and better experimental techniques that can measure all contributions simultaneously. Let me give you some practical design rules that working engineers use. Rule 1. Design your device to stay in a regime where one mechanism dominates. If you need ACEO, use low conductivity. If you need electrothermal, use high conductivity. Avoid the transition region. Rule 2. Use frequency as a control knob. Frequency lets you turn mechanisms on and off. Sweep frequency to find the optimal operating point. Rule 3. Always measure. Simulations are useful for guidance but cannot capture all real-world effects. Build a prototype early and iterate based on measurements. Rule 4. Expect device-to-device variation. Surface roughness, electrode aging, fabrication tolerances all create variation. Design with margins. Let me briefly mention some recent research frontiers in this area. 3-dimensional electrode structures are being developed. By shaping electrodes in 3 dimensions, you can create highly controlled flow patterns that would be impossible with planar electrodes. Active feedback control is another frontier. Measure flow in real time, adjust voltage or frequency to maintain desired flow. This compensates for drift and variation. Machine learning is being applied to flow prediction. Train neural networks on simulation or experimental data. The network learns the complex coupling and can predict flow much faster than full simulation. Hybrid mechanisms combine electrokinetics with other forces. Magnetic fields, acoustic fields, optical forces. The combination can create unique capabilities not possible with any single mechanism. Let me summarize why this problem matters beyond academic interest. Microfluidic pumping is critical for lab-on-chip devices. These devices promise point-of-care diagnostics, drug delivery, chemical synthesis. Reliable pumping is the enabling technology. Understanding the mechanisms enables optimization. If you know which effect dominates, you can design electrodes, choose fluids, select frequency to maximize performance. Separating mechanisms reveals fundamental physics. These phenomena involve coupled charge transport, fluid mechanics, and heat transfer. Understanding their interplay advances our knowledge of electrokinetics. In conclusion, field-driven pumping in real microfluidic chips is a beautiful example of complexity arising from the overlap of multiple physical mechanisms. ACEO, electrothermal, induced charge effects all respond to the same applied field but through different pathways. They have different scalings, different frequency dependencies, different sensitivities to material properties. Their interplay creates rich phenomenology but also makes prediction extraordinarily difficult. Progress requires combining theory, simulation, and experiment. As our understanding deepens and our tools improve, we are gradually mastering this complexity. The payoff will be a new generation of microfluidic devices with unprecedented control over fluid flow at the microscale.